Hi, I'm Nadilla, and this is my Physics 2212 Lab 4 video, Magnetic Field of a Bar Magnet. The purpose of this experiment is to measure the distance-dependent magnetic field of a small bar magnet to compare observed versus predicted distances from on-axis and off-axis magnetic field. A preview of the main results are n, which is a slope, is equal to negative 2.0012, and the magnetic dipole moment nu is equal to 6.398. The principles used are Biot-Savart's law, which is used to calculate current generated by a current carrying conductor. So dB is equal to nu naught times IDL times the unit vector divided by 4 pi r square, where dl is the length of the conductor and I vector is the unit vector which specifies the direction. The magnetic field of a dipole, which it is a closed circulation of an electric current system, and the distance dependent formula, which is the magnitude of a magnetic field due to a bar magnet which falls off with distance. So this is the procedure for the experiment. So the system is the bar magnet, the surroundings are everything else. So the first step is to place the phone so that the magnetometer is orthogonal to the Earth's magnetic field. Find the location of the magnetometer on the phone by sliding the phone along the ruler with the bar magnet on the other end. And finally, to measure the distance between the magnetometer and bar magnet for on and off axis. And you could see the gray object is the bar magnet, and then the phone is black with yellow pieces of tape on it. So next is the data analysis for on axis. So on the top are the distance measurements for the various magnetic field strengths, and on the bottom is the linearized plot of the averages. So we can use the distance dependent formula to find the variables where n is the slope and ln k is the y-intercept. Next up, we calculate for nu, and we use the distance dependent formula and we equate that with b vector, and n is the slope, ln k is the y-intercept. We solve for k and we isolate for nu, and I got nu as 6.398. This is the data analysis for off-axis. So we move the magnetometer perpendicular to the axis, and the x, y, z components of the perpendicular distance, the average is 0.122. Next is the computational model for the initial conditions. So u naught over 4 pi is 1 times e to the power 7, and magnitude of nu that we calculated was 6.398. And finally, we create a function to find the magnetic field. This part of the code is for the visual components. So I specified the magnitude and direction of 2 on-axis arrows, which is in orange, 3 off-axis arrows, which is in blue, and 1 arrow which is 45 degrees to the axis, which is in pink. So the predicted magnetic field is B at 45 degrees at distance d, so that's approximately 6.22, 1.86, 0. So that's similar to the observed magnetic field. And as you can see in the code, the perpendicular distance, the average is 0.122, which we talked about for the data analysis for off-axis. Next up are the assumptions and sources of errors. So the assumptions I made are the bar magnet acts as a dipole, and as distance increases, the magnetic field falls off. The errors I could have encountered are the location of the magnetometer may not have been precise, and the magnetic or electronic objects in the surroundings may have impacted the magnetometer data. Next up is observations. So which statements describe what you observed. So we're asked to find out which is true and which is false. So number 1 and number 4 are true as they follow the distance dependent formula. Finally are the discussion questions. So the first question is, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So the answer is the Earth's magnetic field would have interfered with the bar magnet's magnetic field, which would skew the results. The second question is, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? So the answer is the magnitude of the magnetic field would double, but the direction would stay the same. Thank you.